Hi everyone, welcome to this new lecture. Today we are going to basically cover a few topics, mainly related to how does Linux and Windows do process management. And by process management, how do you create a process? How do you pass parameters to a process? How does the parent deal with the process? You might have actually taken a bit of this during your past courses, but the idea is basically to refresh your minds, and this will be actually crucial for the rest of the course. And by the way, I changed the camera, so I hope that this doesn't result in worse experience. So if this camera is worse, please tell me. Anyway, so the few questions that we are going to answer today is basically how do you build an interface that enables the operating system to work with with any processes. Uh, as we said last time, we have processes that is like the applications that are running, and the operating system needs to manage them. And you need an interface to do that, and that interface is needed to create the process, to communicate with the process, and so on and so forth. And then the question that comes next is basically uh, what kind of powers do you give to the new process? Does the new process start another new process? Can they start processes? Can they talk to different I/O subsystems? Can they stop another process? Can they communicate with another process, and so on and so forth? And then these basic operations requires an interface, and that interface is basically very design dependent, so there is no silver bullet. Every operating system takes some decisions regarding this, and we are going to basically talk a bit about Windows and Linux and how they handle this. Uh, and we are not saying that there is one single correct method. There are methods that are easier to deal with. There are methods that are harder to deal with. But each one has its own merits and has its own strength. And at the end of the day, you cater for different trade-offs. So if you are running Linux on an embedded system, it's very different from if you're running Linux uh, for for a server. And in some sense, the difference comes from the environment, right? So you have different trade-offs. But the way that Linux manages this process creation, for example, is universal across these different platforms, basically, versus other operating systems which will take the trade-offs in the system as an input to how they do the process management. So uh, let's just look a bit at what the programming interface looks like. You basically have your top tier has like few of the different applications that run on your computer, and then you have a portable operating system library, you have the system call interface, you have a portable operating system kernel, and you have the architecture that lies beneath. And we are now going to talk a bit about the system call interface and the portable OS library, as these are the topmost layer that enables different processes, different users to communicate with the innermost parts of the kernel. And you need some characteristics in such an interface. To have an interface that is usable by people, then you need it to be flexible, and that basically means that you need one stable interface that allows you to use it regardless of the version of the operating system. Because that basically means that your applications that you design over here on top will run no matter no matter if you change the system. And this is something that you see in, for example, most Windows or Linux based applications, but you also see that, for example, some of the old, very old games like Prince of Persia 1 and like Double Dragon, and I mean these are ancient games from the 80s and early 90s. You see that they do not run easily on Windows, because sometimes you need to change the whole interface if you're changing the operating system. Nevertheless, a lot of the stuff that used to run back then still runs today. So there is still some portability in the interface that has been used. So you want flexibility. You want basically to be able to go from Windows 7 to Windows 8 without risking not being able to run your MATLAB, which you paid a few thousand kroners for. And then you want it to be safe, because this is basically the interface between you and the users. You as a kernel, you're not. So this is the interface between the kernel and the users. So you want it to be safe, such that it cannot be a source of malicious activity on your computer, for example. So you want to be able to control the safety of that and make sure that it's top tier safety basically. You want it to be reliable, as one little bug in your kernel can mess up everything from your user data to your own kernel to even the hardware. You can actually break the hardware using if you do things the wrong way in the kernel. And if you are not reliable, then you also are not mostly safe. And there are different philosophies to do this. The Linux philosophy uh, is is a bit different from what is called microkernels, for example, and we'll talk about microkernels in a bit more details later. So microkernels, basically, the philosophy there is that you do less coding, you make less mistakes, and you expose less vulnerabilities in your system. So the microkernels is an idea that has very strong fan base, and it's basically that you keep as much as possible outside of your kernel, and you keep your kernel minimal. And a good example of this is an operating system that started as a toy operating system for people to play with. It's called Minix. It was actually an educational operating system for basically giving courses on Linux or on operating systems, and on some. It was actually the. It actually appeared before Linux, and it was a toy operating system for educational purposes, and it is actually a predecessor of Linux. So Minix was the start from which Linus basically began coding Linux, and he diverged and diverted from the way the Minix operating system is built, which is basically as a microkernel, to right now the current Linux philosophy, where you have a lot in the kernel. You have a few million lines of code in the kernel. So, given that you have the reliability property, it's useless to have reliability, safety, and flexibility if your operating system is non-performant. If you cannot get performance out of this, if you can hardly run one single application on your operating system, because one way to basically enforce one way to enforce reliability would be to introduce a lot of, for example, cryptographic algorithms here and there, and introduce a lot of security protocols, and basically try to do optimal scheduling and try to do a lot of things that makes your system very reliable, very safe, but very non-performant. And this is something you do not want to do, because if your operating system is something that serves few million requests per second, then you want it to be able to serve all requests very fast for a web server, for example. But even for a personal computer, you want to be able to run your games together with your Skype, together with your Facebook, without really taking a toll at your performance. And these are basically major trade-offs, and how to balance these four is a question that we are going to answer, hopefully during this lecture. So let us talk a bit more about what process management is. Process management basically allows your program to create and manage sub processes or their own processes. And let me give an example. If you open Firefox, for example, or uh, well, Windows Explorer, whatever, Windows Edge now it's called, or Chrome, then you're starting a process, and that process is basically your web browser. But then you start opening new tabs. These tabs run as different processes for almost all web browsers. So you are creating new processes by just starting a new tab, right? So how do you allow a program like Firefox or Chrome to start new tabs on your system without basically messing your system up? And that's also the case, for example, when you're running a web server, because if you look at Apache web servers, which basically serves almost all, not all of your www requests, but a large part of your HTTP requests go through Apache web servers. And the way that these web servers work is that you have basically a listener, and when you get a new request, you create a new thread or process, and we will discuss the difference between a thread and process a bit later in the course. You create a new thread. Let me use the correct terminology. You create a new thread, and that thread basically starts operating on to serve this request. So the way that you spawn new things, processes or threads, is basically the whole idea of process management. And if we start looking at how Windows, for example, does process management, you have a syscall to create a process, which can be called from your processes, and that's basically called create process. Quite simple. And it basically starts from a parent process, a new child process. I mean, the original process, your original Firefox, is your parent process, but then the tabs you start opening are your children, or the children of the process, of the main process. It's actually it looks quite simple because, well, you have just a call that to create a process, but the devil is in the details, and the problem starts when you start looking at the arguments that you pass to this. So the kernel needs to do the following. When you do the syscall, you basically need to create and initialize a PCB, process control block, that we have discussed the last lecture, or well, in lecture 2. And then create and initialize a new address space for this process, so a part of memory where the process will actually have things running. You need to load the program into the address space, and the program prog here is the first argument that you gave to create process. So you need to create and to load the program prog into the address space. You need to copy args into the memory of the address space, because these arguments that you're passing to your child are probably things that the child will start operating on. And you need to initialize the hardware context to start execution at start. So you need to basically start scheduling that process and the sub process, the child process. And you need to inform the scheduler that the new process is ready to run. And then you also have things such as who controls the I/O, the privileges, the scheduling, and so on. And you also want a way to make sure that your process is actually benign, so it's not malicious. Okay, so you want the syscall to be safe and not to expose the kernel of the syscall of creating the process, and that's basically by making sure that the process is, for example, not trying to access parts of the memory that it should not access, or basically start trying to get control of some hard disk area that it should not access, and so on and so forth. And that results in total that the arguments that are passed are around 10 for create process in Windows, which is quite a lot. And given that each one of them has different permutations, you can easily end up with a few hundred or even a few thousand permutations for just starting a single new process, which is very cumbersome in many ways. But it also has its merits because, well, it's very specific. When you start a process, you can basically specify a lot of things that you cannot specify, for example, for Linux. In Linux, when you start a process the same way that you would do in Windows. Of course, you can do that in Linux, but not the same way that you would do that in Windows, which is basically when you start the process right away. When it comes to Linux, Linux has adopted actually the Unix process management philosophy, which was well, different in many ways, and although it came before Windows, but it's very elegant. And that's basically that when you create a process, you have two system calls instead of one. You have a fork system call and an exec or execute system call. And the fork basically, whenever you create a process, you use these two system calls to basically make things happen actually. And the fork system call basically creates a copy of the parent process, exactly the same copy of the parent process, and makes the child set up privileges, priorities, and I/O. And that basically means that the maximum privileges, priorities, and I/O privileges that the child can get is actually the one of the parent. So it cannot be, you cannot start from a process that has lower privileges. You can start a process from a process that has lower privileges that has higher privileges. Basically, the child cannot have higher privileges than the parent. And basically, as it's the same code as the parent, so since you're just replicating the parent, it is as harmful as its parent, basically. Okay? But once you have the fork, then you start exec, which basically brings the new actual executable of the child in memory. So, I mean, you start by replicating the parent, and you take the parent replica, and then load onto that or override that in memory with the actual executable of the child that should run. And that basically means that that the execute command is the one that actually brings in the new process into being. Fork takes no arguments as input, as it's just, well, replicate the parent, and while execute takes two arguments, which is basically the name of the program to run and arguments required by the program as an array. So if the program requires new arguments to start in, then this is passed using the second argument. And then the parent can call Unix wait, which basically waits for example, a child, for the Linux child for the process child to finish. And you can have also Unix signals, which is basically the system call to send a notification to another process. It's an upcall, the upcalls that we discussed during last lecture. And using these four, you can basically do almost everything regarding process management, including communication between the processes, including what waits for what, locking for different processes, and basically starting new processes from different for different purposes. And this is basically how it looks like. So you have the parent over here, and you fork it, and you basically want to check if you are the parent or the child, because, well, you're running the same code. And basically when you fork a new process, you have a new PID for that new child process, and the parent basically checks if he is this parent or the child, because they run the same code as we said. And then basically once this, if this is the child, then it runs execute to basically bring in the actual code that will run, and execute brings in the main that will run. So this is how simple process management is in Linux, and it's very elegant. It's actually something that was inherited from the Unix operating system, and it is used by quite a few operating systems in general for process management. Now that we have talked about how processes actually create new processes, spawn new children, let's talk a bit about I/O. the input-output interface for the different processes. As you know, a computer is not just the CPU. I mean, we might overstate what we do in the CPU and in the memory in this course, but I mean, the computer is much more than this. You have your mouse, your keyboard, your monitor, your network card, your gaming console, and so on. And each of these devices is very unique. So your keyboard and your mouse are very different from, for example, your screen. They even have different specifications. I mean, keyboard requires to send in one character at a time, versus a monitor, which basically requires to receive, well, the data that can be multiple characters, mostly multiple characters, multiple colors, multiple pixels, what goes where, and so on and so forth. So the size of data expected for the different I/O devices is very different. And basically my camera right now, I mean, this is something that is recording videos, which, well, are a few megabytes per minute, versus basically my mouse, which basically says that this is the differential movement between where the mouse was and where it should be. So I mean, they're very different in nature. One way to handle the input output for the different processes and for the computer is basically to have an interface per device, which would basically require that your different processes will call different interfaces for different devices. So for uh, if I have a process right now, which is, well, the OBS software that I'm using to record video and to basically show my screen and to show also my mouse movement and to record my sound, then this requires an interface per everything that the OBS software uses, and you will need an interface per device basically. And you can extrapolate from this because, for example, my mouse is a very special mouse. I can actually show you my mouse. It's this is my mouse. I mean, no, but very few people have such mice. It comes with, I don't know how many. I said 15 buttons last time. I think it comes with 15 buttons. Yes, and that basically makes it well, not conventional, non-conventional in many ways. So if you have different models, I mean, my mouse, since it's different from your mouse, then we should basically have different interfaces, different for even different mice. And well, this was the way that things were done that in the early computer days. I mean, in the 60s and the 70s, and well, probably also sometime in the 80s, where basically there were very few companies that were making computers, and portability was not really an issue because you wanted people to be locked in to your device, into your computer, and that basically resulted into having a complete mess when it comes to portability. Actually, one of the companies that pushed towards the portability and the kind of easiness that we see right now in using computers was actually Microsoft, and this is one of their great achievements actually, because before that it was just a mess. So the way that Linux deals with the device problem, with the I/O problem, is that it builds a uniform interface, and this was an idea from Unix, which basically got captured by almost all operating systems that we know of today, and that's basically you have one single common interface for all devices and even for inter-process communication. So I mean, even if you have different processes that need to communicate on your computer, they use the same interface, and that is a very simple interface with open, close, read, and write. And the way that open works, for example, and the way that close works, for example, is very dependent on the hardware that you are trying to communicate with, right? So the definition of open, when it comes to basically opening a new file, is very different from the definition of open when it is trying to communicate to the screen, for example, right? But it's from an application point of view, it's exactly the same. It's the same interface. So you can just think of it as open, close, read, and write as a programmer. And what open does is that it returns a handle or a file descriptor for use in later calls. Basically, when you call the screen multiple times, for example, then you will just need the file descriptor, which is kind of, if you're an object-oriented programming guy, then it's basically like you have initialized your object, basically. And open, close, read, and write are all byte-oriented. Uh, you have kernel buffers for read and writes for stream reads, for example. So everything gets buffered so that you as a programmer or the application basically sees the data coming from the screen or the data coming from the mouse or the data coming from my keyboard as basically block reads. So it collects things into a buffer and gives you a chunk of data, and this is the data that you need to actually think about. Okay, just need to shut that down. And that basically also has the effect of masking the different write read speeds of different devices. I mean, your CPU can read in, well, nanoseconds almost, right? Versus your hard disk, which has mechanical things rotating and cannot really do anything better than in milliseconds or microseconds, well, milliseconds mostly. Okay, so the difference in the speeds are masked by having buffers. So if you are a very fast device, then you wait until the buffer is filled, and then you read into a block, a chunk of data. And that means that if you are a very fast device, like if you are the CPU, basically, you can actually operate in such a way that you run for some time doing something else until the buffer gets filled, and then when the buffer gets, when you can read the block, you go read the block, operate on it very fast, and then go back to another thing. And then the one of the important things is that you need an explicit close. So you need to close your connection to basically garbage collect any open file descriptors, so that you do not have open files that are supposed to be interfacing with different IOs, for example, while doing nothing. And I can give a very practical example of this. So right now I am recording using one of the programs that it's called OBS basically, and it captures the video from my camera, right? If I try right now to do a Skype video call, I will not be able, or the other party will not be able to see me, because right now there is an open file descriptor that basically blocks the camera to OBS. But if I shut down the program, or if I basically explicitly close the this connection to my camera, then I can basically come back and make new video calls. Okay? And as we said, open and close and read and write are Swiss knives. So open returns just a file descriptor, and then what does that do is very dependent on in which context we are talking about open. So if I ask you what does open do in a very, very general context, besides making a file descriptor, you cannot basically say anything. Because, for example, if file does not exist, you can return an error. Okay. If file does not exist, you can create file and open it. The same with the same open command. If file does exist, you can return an error. If file does exist, you can open file. If file exists but is not empty, nix it, then open. If file exists but is not empty, return an error. So these are all different and various basically natures of open. And the question can be basically when is when. So basically, when does open behave like this? When does it behave like that? Can you think of examples when open behaves in these different ways? Okay. So Unix pipes, I mean, you have dealt with Unix pipes, and that's basically the buffering part that we have been talking about. You basically have a producer and a consumer, and the producer is one of the devices that writes to a buffer, and the consumer is one of the devices that reads from the buffer. And this is basically the continuation of the open, close, read, write. And you have a buffer that basically buffers stuff based on the speed um, of your devices. Then this buffer gets filled either faster than it's read or slower than it's read. And if the buffer gets filled faster than it's read, then it's problem. It is a problem, right? So if you then you get performance loss, because what happens is that the producer is producing a lot more data than the consumer can actually consume, and then the buffer gets overfilled and you lose data. But typically, I mean, things writing to these buffers are typically slower. So you have the CPU, which is absolutely the fastest thing on your computer, that typically consumes this data from the kernel buffer. So and the pipe gets terminated once either endpoints close the pipe or exit. So I mean, if you no longer are reading from the buffer, then basically there is no need to produce stuff, and vice versa. If you're no longer producing anything, then there is no need to actually watch the buffer. So you basically this is the read and write processes in Unix when it looks when you look at, like, for example, Unix pipes, and this is what Unix pipes kind of do also. So also this is quite similar to the client server model, where you basically have a client and a server. The client is typically reading or writing. I mean, let's talk about, for example, a web server as a server. And the web server contains data, for example, your Cambro or your scalable learning accounts, and you are basically trying to read stuff from there, and that's maybe the videos or the slides, the lecture slides. So you're trying to read them, and when you read them, basically the server puts them in a buffer and you read through that buffer. But you might also be writing, like answering the questions that we pose, or writing notes, or writing feedback on Cambro, and so on and so forth. And then basically there's a buffer also that writes before it writes to the server. And that's basically to have enough data to process. So, as I've already talked, that the Linux philosophy is what is called is very different from what we call microkernels. The Linux philosophy is called monolithic kernels, and they are the most widely used operating systems on Earth because, well, both Linux and Windows are monolithic, and that basically means that lots of functionality goes inside the operating system. Some people argue that, well, we are not using monolithic kernels, we are using a hybrid between monolithic and microkernels, but this is by definition not true, because a microkernel is supposed to be a minimalistic kernel, a very small kernel, and I mean, from a very theoretical point of view, it should be a few thousand lines of code, not a few million lines of code, because it just operates on the very basics that a kernel needs. Versus most of the kernels that we are using, most of the operating systems that we are using, which have a few million lines of code, which are basically Linux, Windows, and the likes. So they are not really, they cannot really, I mean, I do not believe, well, let me put it that way. I do not believe that you can call them hybrid, but a lot of researchers, I mean, the top people in the field, believe that you can call them hybrid. But one of the most philosophical people on this is Tannenbaum, and he does not believe that there is anything such as a hybrid between a monolithic system and a microkernel. So monolithic kernels, they are the most widely used. Lots of functionality goes inside the operating system, and there are two central ideas in monolithic kernels. The first one is that you have a hardware abstraction layer, a HAL, and a dynamically loaded device drivers. Okay, and the HAL is basically a portable interface to machine-specific operations. So you have the hardware abstraction layer has two sides. The top side, which is basically talking to the kernel, should not change. This is basically very fixed, very stable. And the bottom part, which basically talks to the actual hardware, is what changes based on the hardware that you're running on. And that basically means, for example, when you're running on an ARM processor, an ARM64 processor versus an x86 processor, you will have the same top layer of the hardware abstraction layer to which the kernel actually communicates, but you'll have a different layer for the x86 for different architectures in the x86, for example. So if you have an old generation i7 versus a new generation i7 versus an ARM64 processor and so on. And this also, I mean, this is pretty natural since you have different hardware capabilities for different processors. Some processors, for example, come with what is called a co-processor that helps the processor in doing some stuff, or a floating point processor, and so on and so forth. And you always change the lower level of the HAL instead of everything, and instead of basically changing everything in the kernel. And when you do that, of course, you need to recompile, you need to flush your new operating system on your on your hardware. So another central concept to how modern operating system, monolithic operating systems deal uh, dri- uh, with devices is the idea of dynamically installed drivers. And these are basically the drivers that you install for your screen, for your headphones, for your mouse, for your camera, and so on and so forth. And the idea is that you basically plug, and then recently it became plug and play, where you basically just plugged something into a USB, and then it basically searched the entire system if it has the drivers already pre-installed, and if it did not, then it would just download them from the internet, right? And it used to actually be called plug and pray when Windows first installed that, because well, it almost never worked for anyone. And in monolithic systems, these device drivers, they run actually in kernel space mostly, but they can actually run in user space and in virtual machines, and for some new experimental operating systems that people are research kind of operating systems, more more researchy than well, the Linux, for example. So with this concludes what I wanted to say about monolithic kernels, and now we shift to basically microkernels. So let's start to talk a bit more about what microkernels are. I mean, now we have covered a lot about monolithic kernels. Now let's start discussing what microkernel is. And a microkernel is a concept that basically started maybe 20, 30 years ago. It's pretty ancient, and it basically looked at the current operating system stacks, the way that we are designing operating systems, and it showed that, well, there's a trend that everything is going into the operating system, making the operating system bloated. And if you look at this is actually a figure that shows the numbers of lines of code in the Linux kernel over the past few years, actually over the past almost 12 years. And you see that, well, uh, it was kind of low with a relaxed definition of low, but then all of a sudden it started increasing, and boom, it exploded into a few million lines of code. And this is problematic because this basically makes it very hard to, for example, establish things on how the kernel is secure, for example, to establish things on how buggy the kernel is, and so on and so forth. And again, this graph, so that people do not get confused, this is a graph for the number of lines of code in Linux. It's not for a microkernel. And basically Windows has today over 50 million lines of code. So it's just undoable to continue like that. So the idea that the people who basically advocate for microkernels is that you should keep as much of what is not in the operating system, or basically you should keep as much as possible of your operating system outside your operating system and run it as user level services basically. And that includes, for example, things such as drivers. So right now when you look at the Linux code that we have taken a look at on Friday and basically during the past few videos, then the Linux code has a folder that's called drivers. And the idea behind the microkernels is that no, drivers should not be part of the operating system. It should never be added. It should rather run as user level services. Similarly, the network stack would run as a user level service, the file system would run just as a user level service, and you would keep the operating system to a minimal. I mean, you literally strip it from anything that is not core into the scheduling, for example, of the processes, starting processes, stopping processes, and these things. But otherwise, I mean, anything else is just outside of the scope of the operating system. And to communicate, you just need to use system calls instead of basically having the whole drivers or the network stack as part of the kernel, the core kernel code. And this way, you can basically get a kernel that is just a few thousand lines of code. You can actually get it, I think, from 5,000 to 30,000 lines of code. You can get a full kernel, fully functional kernel on which you can run. And Minix is actually such a system. It started as an educational operating system. I have talked about that in very lately. But Minix started basically as an educational operating system that was basically trying to push this idea. Right now, Minix is no longer an educational operating system. You can still use it for educational purposes, but it is actually more, or its authors are trying to push it as a full-fledged operating system that you can use on your day-to-day life. And microkernels, while not popular for servers or for your computers, they are extremely popular in things such as embedded systems and highly secure systems. For example, in the defense industry. So if you are building the next warship or the next fighter jet, what you do is that you do not want to get Linux with its 30 million lines of code and potentially 30 million bugs in the 30 million lines of code, because, well, that's how you operate in these environments. You basically operate under the assumption that the adversary, your enemy, will just try to take control of your warship as soon as he can, right? So in that case, you want something that is very minimal and that you want to prove its security. So people in the defense industry, they don't mostly use monolithic kernels. They go for microkernels, or even what is called now unikernels sometimes. And running on these very bare minimum operating systems, they can actually go and get a few of their developers to work on actually establishing and security hardening these few thousand lines of code, instead of getting thousands of developers to harden 30 millions of lines of code. And these people, for example, they used techniques such as formal methods from computing science to basically, and from mathematics also, to formally verify the security of the system. So they really take it to the edge. And some of this is actually published work. So it's actually available on the internet. It being in the defense industry, being part of what operates your war machines, doesn't mean that it's a secret. It's actually, you can search on Google Scholar, for example, on things such as formally verified operating systems. And basically you take that and you work with this. Well, this is very nice, very well suited for warships and fighter jets, where you have a very specific purpose for your warship. I mean, your warship is not going to change to become a game console, right? So you can optimize on this level. But microkernels suffer a huge drawback when it comes to general purpose computing things, such as, for example, your laptop. I mean, your laptop right now, my laptop is basically a presentation and recording device, but in a couple of hours, it might be a gaming console, it might be my MATLAB simulation environment, it might be my matrix computations environment, it might be just my video streaming environment. So I mean, it runs in a variety of ways. It has multiple natures, and it's really hard to optimize for these natures. Especially that in microkernels, what you do is that you use system calls to have the communication between the processes, because right now, for example, your keyboard runs as a service in user level, and that basically means that you need to do context switching from user level to kernel mode, and from kernel mode to user level to just type a single letter. And that implies that also for not just for that, if you have a couple of, I mean, if you're typewriting in your editor, and your editor basically runs as user level, and then it needs to communicate with another user level, which is basically the drivers, and I mean, it becomes a mess. Inter-process communication becomes a mess, and that takes a toll on the performance. Although some people argue that you can build things in a much better way, but I mean, that's what we have right now. Also, one very hard question is that what you can keep inside and what you need to keep outside of your microkernel. So if you have a microkernel that's going to run on your PC or on your laptop, what makes it what is so important that it makes it to the kernel level code, and what is less important so that you move it outside, right? So I mean, okay, you're going to run your mouse as user level, but are you going to run your hard disk as user level? Are you going to run your camera as user level? And if you're running your camera as user level, then I mean, from one point, security becomes the problem of the driver developer, right? I mean, it becomes easier and harder in some senses because, well, it's user level, so people will try to control it and basically take snapshots of you while you're unaware. But at the same time, it's user level, and thus the driver programmer, who's someone employed by Logitech or, for example, or some camera company, will be able to actually work on it without all the restrictions that you have when it comes to Linux, for example, on or the Linux development cycle, or what they impose on you as a programmer to use. So, I mean, there are trade-offs that are very hard to solve. And this is basically a summary of the philosophy that Tannenbaum, one of the most key figures in the microkernel design movement, and also one of the most key figures in when it comes to operating systems research in general. Uh, this guy actually graduated most of the top operating systems researchers in the whole world, across the whole world, and he is located in the Netherlands. So Tannenbaum, basically, his argument goes such that when you look at your TV, you don't have a restart button. When you look at your kitchen machine, you don't have a restart button, but you have a reset button on your computer, because your computer just freezes and does nothing and goes into these infinite loops, and then it's completely useless. So his idea is that designing a microkernel should enable us to basically build computers that are completely reliable in such a way that, well, it's user space. I'm going to kill the user space process and just continue running, because it's just user space. I mean, if the kernel breaks, it's user space. It's nothing with the actual. If the driver breaks, then it's user space. But right now, if the driver breaks and it's in kernel space, it might mess up your kernel, and then you need to restart. And with this, actually, I conclude this part of the lecture where I have talked about some different design philosophies regarding the process management, for example, what interfaces does process management have, but also some different design philosophies when it comes to basically what do you actually put in your kernel. I mean, you know that the core process management should be there, but should you put the drivers there or not, because the drivers also run as a process. And in the next part of the lecture, we're going to talk about concurrency So I conclude that part, and I will talk to you very soon. So let us start talking about concurrency. And while it seems a bit not related to the previous part, which is the process management part, but what we aim is basically to establish the idea of what is the difference between a process and a thread. And this definition is widely different for different operating systems. So let's delve a bit more into what concurrency is. I mean, concurrency is when, well, you run concurrent things together, and you have them running in parallel, basically. And it's extremely important for you as an operating system developer, and also for the average Joe programmer. I mean, it's not something that only operating systems people need to take care of, but it's also very important for most programmers who go beyond very basic programming tasks. And it's extremely hard to get right. I mean, it's an art, and it takes a lot of. It has a very steep learning curve to actually get right. You have probably studied quite a bit about concurrency before. I mean, or not all of you, but at least a large number of you. I mean, you have all taken the systems programming course, and that course has had a bit of concurrency, but you might have studied it also in your parallel programming course, in your multi-core course, in your matrix computation course. Yes, you might know a bit about that. What we want to emphasize here is that how concurrency is actually implemented down the hood. So, I mean, when you look at the actual operating system, at the actual kernel, how it is actually implemented, and this would help you actually to be better at concurrent programming, right? Because now you will understand, okay, this is the way it's done. And that will help you in your practical parts. So let's talk about concurrency as you know them in threads. And a thread is just an abstraction that is just like a process. And let's look at, for example, when you run Spotify and you also have 125 open Firefox tabs. A thread is basically a single execution sequence, and it's also schedulable. Let's basically talk speak about a bit about the difference between what a thread is and what a process is. And let me say that this is very operating system dependent. For most operating systems, actually a thread is a kind of a process, or is a special kind of a process. So most operating systems, Linux-based operating systems, most Linux-based operating systems, they actually think of a thread as much as they think of a process, and they are just the same. And it's basically the programming model that you use to do concurrent programming, that is, use multi-threaded programming. And each thread you can think of as something that can be scheduled on its own, just like a process. And then the difference between a thread and a process in Linux, we'll talk about a bit about this in more details when we also even look at the kernel code in a later video. But the difference is that a thread to Linux is just a process that can share data with a different process, which is just a different thread basically. Okay, right? So they are just the same. They are dealt with exactly the same, and then they are just as schedulable as any process. Uh, and you can have basically protection as an orthogonal concept to this. So you can have, for example, access control on a group of threads that are basically coming from the same process or from the same parent, sort of. And the question comes is, when do you use threading? And you basically use it when the program structure requires parallelism. So you're trying to do to execute different parts or process different parts of your data in parallel. Or, for example, you have network packets arriving in parallel, or you have a server that runs basically and gets 1000 requests per second, and each request does something different, including communication with the database. So you basically have 1000 possible concurrent things happening, communicating with 1000 possible concurrent clients that are completely in different parts of the world. So this is when you start thinking, this is one of the times you start thinking about threading. Sometimes you also want to basically, or you're able to shift parts of a program to run in the background instead of having the whole program running continuously, but you might think of some parts that are, well, less important of the program. And you basically, you shift these parts of the program to the background, and you do that by basically implementing them as threads, as background threads that runs in the background. And well, these can, I mean, you can prioritize threads based on how important they are in your program and so on. But I mean, you can think of them as a way to basically, okay, break your code into different parts, and just say that these parts will run in the background. This is, for example, my graphics card in the this is my graphics generated for the game. Then this should be in the foreground and so on. You might also think of them when you have multi-cores. And actually, a lot of the multi-cores come with a twist. So multi-cores CPUs, for example, the Spark CPUs, the Spark multi-core CPUs, per core, they have different threads that can run per core. So you can actually run 4 threads on a single core. And that basically, if you have, means that if you have 8 cores, you can run 4 multiplied by 8 concurrent threads at the same time. But in general, in your x86 architecture, you basically have 2 cores, 4 cores, 8 cores, and then you can run 8 multiple things in parallel, and thus do 8 things in parallel for the same program. So, and that comes very handy, for example, when you talk about big data analysis, for example, I mean, which is a high powered. I mean, you can run 8 different threads on 8 different cores, processing 8 different parts of the data at the same time in parallel, cutting your running time by almost 1/8 of the total time. And I mean, these are these things that multi-core programmers do. And then you have things such as I/O performance. Well, you can run a thread that basically goes and fetches from the I/O something. And I/O, for example, your hard disk, if you have an HDD, it's well, quite slow. Okay, if you talk about I/O in the terms of your keyboard, a normal human can type something like 5 characters. Not a normal human, actually, a professional typist human can type 5 characters per second. That's like, I think the record is like 6 characters per second or something. And that's the maximum you can do. And that basically means that you run a few orders of magnitude, actually a few thousand times slower than your processor, because the Raspberry Pis that we are using, for example, they can have more than 4.7 billion operations in 1 second. So so you can do 5 characters, and that thing can do 4.7 billion operations in 1 second. So what you want is that you want a thread that basically runs very slowly, getting my 5 characters per second, and that's basically the slow moving, slow motion, versus other threads that basically do other stuff very fast during the remaining 4.7 billion operations, for example. I mean, of course, fetching 1 character is not one operation on a CPU, but I mean, it's like 10, even 100 operations. So I mean, 5 characters, that's 500 or 600 operations per second just for fetching from the keyboard. But then you have the remaining 4.7 billion to play with and do stuff with. So threads is a very neat way to actually do sharing of resources on your computer. And as I said, threads versus processes is very operating system dependent, and sometimes even very architecture dependent, but mostly very operating system dependent. So you have different concepts like multi-threaded kernels, which are basic kernels that are able to run multiple threads and internally in the kernel itself, sharing kernel data structure, capable of using privileged instructions. So your kernel itself runs as threads. It's not your user running as threads, but your kernel itself runs as threads. You have multi-process kernel, which basically runs multiple single-threaded processes. And I mean, these are more design philosophical tags for the operating systems. How does the operating system runs internally? I mean, or what does it support? And well, multi-threaded kernels and multi-process kernels, I mean, they're also explained in much more details in the book, so you can basically refer to the nitty-gritty differences in there. But the main difference is that the first one has multiple threads sharing the kernel data structure, while the second one has multiple single-threaded processes. And then you need system calls to access the shared kernel data structures, so they don't share them directly. And then you have multiple multi-threaded user processes, each with multiple threads sharing some data, but also needing to communicate for other data that is isolated from that shared data. Now that we have talked about the concept of threads in operating systems, and we have briefly discussed how different operating systems internally handle threads, as in the operating system itself being threaded in some way, let's talk a bit more about thread scheduling. And threads basically provide an abstraction of infinite resources to a thread, to the program running on a thread. And that is basically by having the operating system scheduling the threads in such a way that will enable some sort of fair usage of resources among the different threads on these running on the system. And it is quite important that every single thread running on your computer gets some time on the resources, otherwise the thread will be idle and will basically never have the feeling of making any progress. Some threads will be faster, so for example, if your thread doesn't involve any IO operations, then well, you're just touching upon the CPU, and the CPU is pretty damn fast. Also, the memory is kind of fast. It's slower than the CPU, but it's much faster than, for example, you typing on a keyboard or the hard disk. So some threads will in general be much faster when it comes to how they run. And one very important thing to note is that your program should be designed such that you never make an assumption on when and how your thread will be scheduled. So you cannot make an assumption, for example, on which thread will get scheduled before which thread. These kinds of things. And this is very important when you're doing concurrent programming, because you want to make sure that your threads run in the correct way. And you want to take into account that some of the other threads will run much faster than the threads that you have, while some others will be much slower. And this figure basically shows the thread execution model, which is basically the thread thinking that it runs on a dedicated virtual resource or a dedicated virtual processor. But that virtual processor is just of unpredictable and variable speed. So to each thread, it feels like it has its own processor, just running with at different speeds, at stopping and idling and so on. And processors are in general not your bottleneck, because they are pretty fast. If your program is correct, then you should be able to implement your program such that you get enough. Your processor is not a bottleneck. So let us ask a question. I want you guys to reason about the execution of the threads in here. So there are 3 threads, and when do you think that this is possible? When do you think that this execution model is possible? And when do you think that this execution model is possible? Do you think that it's hardware dependent, or do you think that it has to do with the operating system? So let's talk a bit more about the problems that you may foresee already when in the threaded programming model. You have to have preemptive multitasking, so you need to basically be able to preemptively remove some threads from using the resources because, well, they have been running for too long, or because they're blocked on some for some reason, or even because they are just doing things that they are not supposed to do. And you might need to do that while having 4 cores and all 4 of them running 4 different threads. So you have preemptive multitasking. As we said, you should never make assumptions on the speed of your thread, and you should always not also make assumptions about if 2 threads share memory or some resource on who writes first or reads first, unless you explicitly implement this in your program. And we will talk quite a bit about synchronization, about things such as locks and semaphores and so on in the operating system and in concurrent programming. Thread operations they usually have very simple interfaces. Well, thread create, which creates a new thread to run some function. So you basically, this calls a function to create a new thread, and that runs this function with these arguments. Thread yield basically relinquish the processor voluntarily. So you leave the processor voluntarily because you're waiting for I/O or you're waiting for something. Thread join thread, that is basically the parent waiting for some of the 4 threads to exit and then return. So if you are a parent, I mean, just when, like we were talking about process management in the previous few slides, if you are the parent, you can actually start new threads, and they're, well, you just use thread create, for example. And as a parent, you can wait for 4 threads to exit, basically. So you wait until all your threads are done. You start child processes, child threads, sorry, and you wait for them to be done and before you do anything. And then there is thread exit, which basically is the call that thread calls to quit and clean up whatever memory it has been used, and wake up any joiner. So if it had a parent, then it will wake up the parent. There is a thread API where you have basically asynchronous procedure calls. The caller continues execution and does not wait for. So let's talk about the thread API. And the thread API is actually asynchronous. It's an asynchronous procedure call, meaning that when you call create thread, the caller should continue execution and does not wait for a return. That's the default behavior. But then if you want to wait for the child thread, then you basically have to explicitly call thread join. Wait for the uh, children threads that were spawned to come back before you basically do anything. And that might be basically for because the parent is waiting for some results or something. Creating a thread is a different operation from scheduling a thread on the kernel. And by the kernel basically. So you create a thread, but that doesn't mean that the thread gets actually scheduled on the processor when it's created. It just it's just created and kept somewhere and being ready to run. So let's ask a question. How many times can thread join be called for the same thread? So how many times can you call thread join for the same thread? Let's give an example. I want you to actually take this example and run it. I had a suggestion before to make the slides available for you beforehand so that you can copy and paste from the slides. The slides are now available on Cambro, so you can just copy this example and try it and see what happens. And I have another question for you. What is the minimum and maximum number of threads that can exist when thread 5 prints hello? So you have basically an iterator that prints something and prints basically the number of threads, right? And each thread, I mean, you have 10 threads created in this example, and basically you start you spawn them and you wait for them. So you spawn them in thread create, and you wait for them in thread join, and you basically then in each thread you go in here and do this. You print hello from thread and print your own thread number. So the question is, what is the minimum and maximum number of threads that can exist when thread 5 prints hello? And let me ask you yet another question. I had a comment from someone that basically wanted more questions per segment, and this is yet another question for you. Is this output possible? Basically, can 105 print the return before 102? That's another question actually. So let's go back to fork and join parallelism. Threads can create children and wait for their completion, as we have seen, and basically the data is only shared before the fork and after the join, or after the join basically. So let us now look into the fork join parallelism. And fork join parallelism is basically that a thread can actually create children threads and wait for their completion. And when a thread creates a new thread, or a process creates a new thread, you almost always have the data only shared before fork or after the join. You can, of course, share the data through a file or do something that is, well, not super, I wouldn't say super intelligent, but I mean something that is weird. But in general, I mean, using the thread API, the way you share data can only be before the fork, so right before you actually the new thread starts running, or right after the child thread exits, and then after the join. And there are multiple examples of this. So a web server, and Apache web server, actually runs as the thread that spawns new threads for every new connection. And if you have dealt with Apache web servers before, few of you have done, I know, then what you basically have is that you can run out of connections, for example, because you have run out of threads. Because these are basically hard limits that you can set on your system, because you don't want your system to be flooded with a number of threads that would kill the performance completely. There are other examples, of course, when you do merge sort in parallel. So you can do merge sort using threaded programming. And for this, please refer back to any of your data structures or algorithms books or courses. And things such as parallel memory copy, when you try to copy different chunks of memory at the same time in parallel. With this concludes today's lecture. This is the reading guide. We have actually covered chapter 3, the whole part of, except for 3.4 basically, and a large part of chapter 4 has also been covered. I will also record new videos today for the lecture. So this is the lecture that is for Tuesday. I'm sorry for the delay, but I will also record next Friday's lecture today, and also some of the Linux hands-on lectures that I started will also be recorded during today and tomorrow. I promised that there will be a lecture on architectural concepts. I have actually checked it out. I know that half of the students are in a program which does not require architecture as a course basically. So you probably know less than some of the others in the course. So I will record a video with hopefully it will not be longer than 2 hours. With some of the major architectural concepts when it comes to the CPU. I hope to be able to do this week. You will not everybody needs to watch that, of course. I mean, of course, it's nice to basically have refreshment on what the processor looks like and so on. But I mean, if you know this stuff, if you know what a program counter is, then just don't bother at all. But if you don't, then it would be nice to watch the video. I'm not saying that it will hurt you in any way to not watch the video. So it's not compulsory to know this beforehand, but it's kind of nice to basically know what is the difference between MIPS and, for example, and what are these different terms? RISC architecture, CISC architecture. I mean, these are very different. What are the major differences that you would expect from a different architecture and that can influence an operating system? So you can view this as the architecture video as a way to basically help you refresh your minds, but also to help you put things into context and get a hopefully better picture on how the full computer stack works. Thank you, and sorry for the delay with this lecture.